looking at G-GMD, which is basically geometric measurement and dimensions. And we're going to look at the basics of area here, building it up to volume. So the most basic shape that we know for area is a rectangle. And one of the nice things about the rectangle, at least in this kind of format, is that when you're talking about area, you're talking about how many squares, whatever the units are inside of the shape. And because of the rectangular shape, whatever whatever the increments are of these squares, it's a very arrayed approach. In other words, it's this length or width times 1, 2, 3, 4, 5, 6, and we talk about 18 units squared, because whatever the measurements are, that's how many squares there are, how much space is filled inside of it. And because of that formula, we now build to all of the other formulas, triangles and parallelograms and rhombuses, all of the other guys that are coming. But they're all built on this idea of the original guy just being length times width, if you want to think about it that way. If you want to think about it as base times height, that's also a nice way to do it, but a very simple region to calculate. From there, we begin to then say, how can we obtain the other formulas and use this as the basis? So a parallelogram, I think most students quite immediately see a connection between these two, that their formulas can be quite synonymous, actually. And the first way students see it is by way of dissection. Much like if you're in the biology class and you're dissecting the frog or whatever, you're taking pieces or parts of that object, okay? And you do the same thing in geometry. So in other words, this is our base, and this is our height of our parallelogram. And you can kind of see, even by the way I've drawn that, a very nice way to dissect this is that if I took this region here, it would fill this region exactly. And it would form a new shape. And again, maybe let me take this out of the picture here. It would form a new shape, which would be a rectangle. Now that rectangle, let's look at its dimensions compared to the original parallelogram. The base used to extend out here, but we noticed, wait a minute, the part that we got rid of showed up again. So the base is unchanged. That base is still the exact same original measurement. And the height is unchanged of the parallelogram to the new rectangle. So we found out that the formula for a parallelogram is also just simply the base times the height. This dissection technique is just a nice way to show it or demonstrate it. Another technique for learning the area of a parallelogram is something called shearing. And the idea of shearing, let me write it down for you, shearing is a process where you lock in a single dimension, and so in this case we would lock in our base, so this is unchanging. And then what we're going to do is move the opposite side in a parallel manner. In other words, I'm going to allow that to slide or shear back and forth. Now, as long as it moves in a parallel manner, as long as they move in a parallel manner, there will be no change in height. So we'll demonstrate this on a computer in a minute, but I think you get the visual idea. Is what I'm going to do is simply slide this along this parallel line and stop it right when I am above the other location. And so when I'm done, I have sheared that parallelogram into a rectangle. And that rectangle is also just the same base and the same height. In other words, the formula for a parallelogram is base times height. We'll just demonstrate a couple of shearing examples for you. Let's take a close look at area and this idea of shearing. So here we have a base of 4 and a height of 3. They're perpendicular to each other, and so the area of the shaded region of the parallelogram is base times height, which is 4 times 3 times 12. Now the idea of shearing is that, let's say if we locked this base and we only moved the top. Do you see how I'm moving it in a parallel manner? So my height still is 3, my base still is 4, so the area is still 12. So this parallelogram has an area of 12, so does this one, so does this one, and so on. And so you can shear it until it's a rectangle, and it's quite easy to see its base times height is 12. So this is a nice way to get an idea of the relationship between shearing and area. If you shear along a parallel manner, you maintain the same area. Also, let me just quickly demonstrate the idea of dissection to you. The idea is to take apart one shape and make it into one that you're more familiar with. And so I'm going to cut this triangle off of the parallelogram and bring it over here. And now if you look at the new shaded region, it's a rectangle. Its base is 1, 2, 3, 4, which is the same base as the old parallelogram, and the height is the same. So again, this is 4 times 3 for an area of 12. That would mean that this is also 4 times 3 for an area of 12. So the idea, we can dissect it and move it over into this region and form a parallelogram. Sorry, actually a rectangle here in the exact same area as the old one. And so it's what allows us to call it dissecting from here into this position.